Come on, settle down, please. All right. Where did we left off? All right. We left off at, I think, the energy equation looking something like this. P1 on rho g plus V1 squared on 2g plus H1, say this is 0.1, this is 0.2, plus any, if you put any turbine, so H turbine, no, pump, sorry, equals to P2 on rho g plus V2 squared on 2g plus H2 plus head loss plus head turbine, if you have any turbine now. All right, and you want to convert this head to power. Power is equal to m dot g h. Again, that could be pump, it could be turbine, it could be loss, depending which one you want to look at. All right. Hey. Attendance today very good, huh? All right. Okay. So we did up to there. Any questions? You okay? So this is basically energy going in, and this is the energy going out of the system. All right. So energy conservation, first law, in equals out, steady state. All right. So steady state, this is the equation. And so far we had head loss is equal to F L on D V squared on 2G plus sum of all the minor losses V squared on 2G. Okay, that's how we defined it. And for F, alright, if it's laminar flow, if the Reynolds number, alright, F, okay, if your Reynolds number is less than 2300, then your F is equal to 64 on RE. If more, then you need to find the relative roughness and look up Moody chart. Is that alright? So this V is not V1, it could be V1 or V2, but this V is the velocity in the pipe. Alright? V equals to V average in pipe. Alright, the average velocity. Alright? Okay? Which basically your that V m dot equals to rho A V average. Alright, so that's the average velocity in the pipe. Okay? So everybody okay with this so far? That's what we did on Thursday before then the break. Alright? Hopefully you looked at it a little bit during the break. Okay? So, and RE is equal to rho VD over mu. Alright? So, any pipe flow problem, normally first step you calculate Reynolds number, then you decide whether laminar or turbulent. Alright? If it's turbulent, if laminar, you can look up like this. If it's turbulent, you have to look up the Moody chart. The Moody chart, I thought you have to look up, is a logarithmic scale at the bottom. And you also need to choose the relative roughness over G. You need to find the relative roughness and then look at the appropriate line. Alright? After that, you can find the F, which you then can put in here, and then find whichever is missing in the equation. Maybe you don't know what the pressure loss is or something like that. Okay? Or any other parameter that's missing. Okay or not? Any questions? Alright. So, and we'll do some practice. I think this week's tutorial is on pipe flow. Alright? So, okay. What's that one? Yeah. So, it's okay. Alright? So, problems, where you know V and you are given velocity and diameter, you can work through this way. Alright? But let's say if the problem asks you to find the velocity. Alright? Okay? If problem gives you V and D, then no problem. Okay? That's the way we've done. Alright? It's no big problem. Okay? We follow this procedure, find Reynolds number, look up, or find F, and so on. Okay? But if problem requires finding V or D, how? Okay? In recent history, exam problems don't tend to be like this. Right? They want to do easy. It tends to be like this. How? Okay? So, not both. Cannot find both velocity and diameter. It's one or the other. Alright? So, okay? Or, not both. Alright? So, in that case, big problem, isn't it? Alright? You know why big problem? Big problem because first step already start, cannot find Reynolds number. Cannot find Reynolds number, then cannot find F. Cannot find F, then there's one unknown floating around your energy equation. Don't know, cannot. Alright? So normally, and we'll do this, I think, got tutorial problems, and if you do past year problems, this one occurs. Alright? Need to guess. Alright? Let's say if you want to guess V or D, alright, you need to find one. I cannot be trying to find both, because then your problem is just too loose. Alright? So if, example, alright, if let's say D not given, alright, then you need to guess the diameter. Alright? With the guess diameter, okay, so e.g. D equals, don't know, unknown. D given. Alright? So you need to guess the diameter. Alright? Then find RE. Then find F. Find F and possibly E over D. Alright? Hey. Find F, find E over D, find F. Okay, from Moody chart. Okay, or if laminar flow, then you can also find from the Moody chart. After that, then put in energy equation. All right. If right hand side equals left hand side, good guess. Else, guess again. Alright? So, do you understand what I just said? So, after you guess the F, let's say that for this particular problem, as the design problem, asks you to select a pipe, so you don't know the diameter. Alright? But you are given all the other things, the P1, P2, and V1, V2, and all that. Everything given except diameter. Alright? So you need to guess the diameter, find the Reynolds number and the relative roughness, look up the F from the Moody chart, put into the energy equation, means put inside here. Put back inside this equation. Alright? This is the energy equation. Alright? And if this side balance this side, then it's a good guess. Alright? Means your system conserves or satisfies the first law, satisfies the energy conservation principle. Alright? If you put a wrong guess, alright, then you look up, then your Reynolds number and so on, then your F may be too high. Alright? Then you won't balance. or you guess the velocity too low, F will be too low, alright, or something, and then the velocity won't balance again. Is that alright? Okay? So that is alright, if problem requires finding V or D, you can guess V or D. Once you guess one, if you know the, or you have, well, depends on. You may be able to work out the velocity, normally you are, alright? Give you a velocity, ask to work out the diameter for a given problem or so on, alright? Anything that does not have the velocity or diameter requires a guess, alright? And then work through the problem and see whether your energy equation balance, okay? We'll do practice problems, that one takes quite a while, because guess wrong, then have to do again and again. So, we do practice problems in this week tutorial. Okay? Is that clear what I just said? Alright? Is that okay or not? Any questions? Alright? Yeah, since this problem normally takes quite a while, I'll do it during the tutorial. If I do it here, might take 2 lectures or so. Okay. Any questions? You okay? Alright. So, up till now, the head loss, we've only considered the pipe. Alright? I told you this is normally considered the major loss, and this one considered the minor loss. Alright? So major loss, F, right? F is the units of kinetic energy loss per diameter of pipe. Right? L of D, so for 1 diameter of pipe, L of D is 1. Number of kinetic energy loss. Alright? K is the same. It's the number of kinetic energy loss, number of units of kinetic energy loss for when the flow goes through a given fixture. So a fixture could be, there could be so many. There could be an elbow in the pipe. There could be a valve. All right. There could be entry into from the pipe to the tank, or from the tank from the tank to the pipe. So entry losses, or for when the pipe enters the tank. All right, and so on. All right. When the small pipe goes into a big pipe, when a big pipe goes into a small pipe. There are a lot of games on all the iPad and all that, play pipe one, isn't it? Okay. So see, you play some of those games, you know all the accessories. Okay, any other pipes? Okay, so normally there's a lot. I think there's a whole table in your textbook, all the different one. So normally for each one, you can look up what the losses is, all right? Or in an exam question, they'll tell you what those losses are, then you just add them up. You just include them. They say elbow loss 1.5, they say and got 3 elbows, then you have to add up 1.5 plus 1.5 plus 1.5. All right? So you just add up all the minor losses. So let's see what minor losses. So KL all right, which is equal to the number of units of kinetic energy loss going through fixture okay, then I brought up here, hopefully it's here. Okay, so one, okay, so like valve, all right. So this valve special, all right. Because valve you can adjust on, you can open the tap, you can close the tap. So the KL in this case is a variable, all right, depending on the valve position. All right, if you open the tap fully, then the KL is very low. If you close the tap, except not completely closed, but just a little bit opening, then the KL will be very high. All right, that's how it actually regulates the flow, by adjusting the losses through the pipe. All right, by either making a very big opening, very small losses, a very small opening, forcing all the flow to go into a very small path, that causes a lot of losses, and that the whole system adjusts to that. All right. Okay. So the whole system, I mean, is this equation here. All right. So if this term, the head loss, where's head loss? Head loss goes up very high. The whole system will have to adjust to balance the energy, and therefore maybe you get very low flow rate now. All right. But we'll talk about the system and the one a bit later on. But that's a valve. Right. Okay. So other losses are like N3. All right. So the losses, you guys already did a little bit of that in the flow measurement prac. All right. Those two flow devices, the Venturi tube and the orifice plate, they had losses there. All right. That's why there's the ideal flow rate and the actual flow rate not the same because there's losses. All right. And that CQ that you calculated is actually a function of the losses. All right. So here, okay. So that's one example. So like a fixture, like a flow measurement device, will generate some minor losses. All right. So in this case, there is a tank going into a pipe. All right. For tank going into a pipe, all right. You can do it a few ways. You can give the number. A number. All right. No, they didn't give. All right. I think for each case here, if you look in the textbook, they give you a number. All right. I think these cases is the highest minor loss, less, and lesser. All right. Because from here it's very abrupt. Okay. Here it's still very abrupt, but at least it's flanged to the wall. Here got at least some curvature, and here even more curvature. All right. So then in this case, the pipe losses, the entry losses is different. All right. Okay. Losses is again due to flow friction, flow turbulence, and so on. When the flow has to accelerate from the tank into the pipe. There are no numbers. Anybody got textbook? See what the number is. All right. You can check what the KL for each case is in your or estimated value is given in the textbook. I don't know why they didn't put. Or maybe here they put no? Here. So, okay. All right. So the sharp corner, blah, and so on. The loss coefficient for a square edge entrance is approximately 0.5. All right. So this here is about 0.5, and it goes down. Oh, there's a plot here. This is KL as a function of R on D. All right. So if you make it more smooth, more rounded, the bigger R, bigger curvature, the KL can go down. Starts about 0.5. All right. Is that okay? All right. So the numbers you can get from the textbook. Any question? So that's tank entering into pipe. I think next one is pipe entering into tank. All right. So in this case, all right. Why we say one? All right. Here is because, all right. Here there is the flow is moving what velocity? What velocity here? Huh? In the pipe? V or your one called. All right. There's not really U infinity because it's a private profile, but at more or less the mean velocity. Is that okay? All right. So here mean velocity here. What's the velocity here? 0. All right. So how much kinetic energy you lose from here to here? Half rho v squared. All right, not. That's why 1 times half rho v squared. Yeah. All right. So you essentially lose v squared over 2g. This is one head unit of kinetic energy. Okay. So in this case, you lose 1 unit. No matter what you do, all right, you end up losing 1 unit because it goes from moving to stop. All right. But some might argue, if you're very smart, there is potentially some pressure recovery from this one, like a diffuser. All right. Well, yes, but normally that if you were to make a diffuser, the length of that expansion will be very long. You need to make it a conical angle around 7 degrees. about 7 degrees to get it to work properly, or so, around that. So normally that doesn't happen. So in most cases, you can assume this is one. No one is going to make a diffuser to end for the. When you're going to enter a pipe into a tank, it's very unlikely you're going to have a nice diffuser there. It's going to be very expensive. And all right, I've not heard anyone do that now. All right, yes, and it has to be very gradual angle to actually get to recover the to properly convert the kinetic energy back to flow energy here. So if you don't convert it, then it's just lost into the big tank. That kinetic energy is dissipated into the big tank. So K1. All right. Any questions so far? All right. Oh, this one. I'll come back to that. So I'm just going to do this one. Okay. So other types of valves. I think each got a number. This is okay. So there are different types of valves. All right. The globe valve. So globe valve has a funny. The flow has to go around this is very common for your tap heads. All right. Your flow has to go around this path, and there's this washer that will squeeze against this hole to close off the flow. All right. So this one, the losses tend to be quite high. Gate valve, the losses tend to be quite low because it is like a gate. So the gate open. When the gate is in the open position, there's hardly any constriction. All right, hardly any obstruction. So gate valve, and the other one is the ball valve. Instead of a gate, they have a ball with a hole in it. All right, the ball can close off. All right, ball with a hole in it, so it closes off, blocks the flow, opens. It also has no disruption to the flow. All right, so gate valve, ball valve is pretty good. Angle valve very rare. This one is a check valve, just to more to ensure that no flow goes in the backward direction. All right, this valve, right, this closing here. It's not quite rare. All right, so the different types of valve, each one, as I said, has a minor loss associated with it. Obviously, this one will be on the high side, and depending on the valve position, the minor loss can change also. All right, if you close it off completely, then the minor loss is infinite. All right. Okay, so here, more picture. All right, you can expand now. All right, so here are more typical values of elbows. All right, some might ask, what is flange, what is threaded? Anyone asking? All right, so okay, so this is a 90-degree elbow. All right, for the pipe, settle down please. For the pipe connection, all right, for the pipe connection, there's two types. All right, there's like your half pipe, they tend to use the threaded connection where you can screw the pipe pieces together. You played before, no? Can screw. All right, for high pressure application, that doesn't work. All right, you put the plumber's tape and then you screw. All right, that's okay for small pipes and for low pressure application. But imagine trying to screw pipes big like this. All right, where you get the spanner so big? All right, so for big pipes and for high pressure applications, all right, the threaded screw joints would not work. So what you have is a flange. Okay, so flange basically, all right, so you have a pipe, you weld a flange here. Okay, the flange is not from here. It look like you welded the pipe shut, but no. Okay, the flange, front view of the flange will look like this with screw holes here. Okay, so you get one flange. All right, you weld it on this pipe, weld it nicely. Okay, well, you weld all around this side. On the other pipe, you also weld the flange head, and then you put the two flanges together, and then you put normally you have a gasket in between, okay, to seal it up, and then you put the bolts through. Okay, not? And then that squeezes the two flanges together. Okay, so that's a flange connection. For high pressure and for large pipes, this is normally the case. All right. Okay, so obviously, okay, as you see, the regular and the long, the long radius is a lot short, the minor losses is less. Alright? If you have a very sharp corner, obviously the losses is more, the flow is have to make an abrupt turn. If you make it gradually turn, alright, then the losses is less. But here, you need to, for one, you need to be able to have the space for it to turn gradually, and also your expenditure will go up because you have a much longer piece of pipe you have to bend. Alright? This one is like your normal, regular one, is like your normal elbow you use at home, your home piping. It's very short one, it's just a 90-degree bend, more or less. Alright, the other one, sometimes you see it's a longer radius. Okay? Okay, 180-degree bend. Yeah. Alright. Okay. They're traded a lot higher than the flange. Huh? Why? Because the flange connection, alright, flange connection basically when the flow goes through it, it doesn't see any obstruction. Okay or not? Alright? Whereas the threaded, okay, normally the threaded pipe, okay, will have a thread. This pipe here, you thread here. Then you have another fitting that screws on top. Alright, each thread is here. And then you have another pipe here, which the threads is here. Okay? So this one, it's the diameters may not exactly match. Okay? So the inner diameter here of this pipe is like this. Suddenly go out bigger. Suddenly then you have to come out smaller again. Okay or not? Alright, so the inner diameter here will be smaller than the inner diameter here. So the pipe, the flow suddenly expand, suddenly contract again. Alright? It's not smooth. Alright? So if you measure the diameter here, it won't be constant. Some parts diameter get bigger. Alright? Where's the flange connection? Alright, once it's connected, there is essentially no change in diameter. This hole is exactly the diameter of the pipe. Right, this whole opening. Okay, so that's why flange connection quite considerably lower than threaded connection. Anything else? Alright. Union thread, right? Even that alone has some losses. Okay, wait. Okay, and then all the different type of valves are. Alright, so ball valve, when it's fully open, right, is the lowest. You see what a ball valve is? Yeah? No. Everybody know what a ball valve is or not? No, they have to find. Okay, ball valve looks like this. Alright? On the outside, it doesn't look that fantastic. Okay? But inside, basically what it is, there's a ball here. I told you there's a ball with a hole in it. Alright? So you can align this, when this hole lines up with the pipe, you get very little disturbance because basically the pipe is just more or less one continuous pathway. Alright? Whereas the other types of valve, okay or not? Alright? So, ball valve. Got big ones also. Alright? Those used in oil and gas industry and all that, and other industrial application, it can get very big. Alright? This is small one for your pipe, water pipe. Okay? Alright. Okay, so, no, I'm not seeing this one. Okay, so ball valve is good because the minor losses are minimal. That's the valve of choice. Alright? Globe valve. Alright, globe valve is which one? It's the worst. This one up here. Yeah. They call globe valve. Alright, globe valve is the worst because the flow has to go, even when it's fully open, the flow has to go around that funny path. Okay. So when it's fully open, it's 10. Okay, gate valve when it's fully open is only 0.15, not bad. All right, and as you close the valve, all right, you can increase the head loss now. You can control it, all right, and that's how it's used to control the flow. All right, increase the minor losses until very high. Okay. All right. Any questions so far? Okay. No. All right. I'll come to this one soon. But before I do this one, I need to talk about something else first. Okay. This is traded now. Okay, so there are two types of piping. All right, we'll do pipe in series first, and then after that I'll talk about pipes in parallel. All right, pipes in series, all right, is basically one pipe connected to another pipe connected to another pipe. All right, pipes in parallel means actually there's maybe multiple paths on. All right, so sometimes the water, all right, is diverted down two paths and then joined back together at some point later. All right. So pipes in series. Example. All right. I have a tank. Okay, this tank is higher than this tank lah. Okay, and then after I go one pipe. All right. Then after that I go to another pipe. I'm just exaggerating here lah. Okay, so this is diameter 1, here diameter 2, here diameter 3. Okay, so this is pipe in series. Alright, they are different diameter. Alright, so maybe here diameter 1, 10 meters of this, 5 meters of that, 2 meters of that, something like that. Okay, so this one, in each case we always start, this is 0.1 and this is 0.2. Okay, so we can write the energy equation as we done before between 0.1 and 0.2. But our head loss, in this case, so this one, depending on your m dot, is equal to rho A1 V1 is equal to rho A2 V2 is equal to rho A3 V3. So for each one, it has a different velocity. Alright? Where the pipe bigger, obviously the velocity lower. Where the pipe smaller, the velocity bigger. Is that okay? Alright, yeah? For a given flow rate going through that. Right? The flow rate which you could determine, but okay. So the head loss is equal to, so for the first segment, all right, K entry times V1 squared over 2G, right? Entry losses here, plus F1 is the friction factor in here, L1 over D1, V1 squared over 2G. So far, you agree this one? All right. So this is the minor losses when the pipe enters, when the flow enters the tank. All right. And this is the major losses for the first segment. Okay, now. All right. Here there's also a minor loss here when you go from a small pipe to a big pipe. All right, or from big pipe to small pipe, or all that. Okay. Anytime there's some disturbance to the flow instead of just a pipe, there will always be some losses. All right. So plus K expansion. Do I take V1 or V2? Okay, well, both answers also actually correct, but the convention, all right, is to take V1. You take the higher one, all right, plus F2 L2 over D2, V2 squared over 2G. Alright? Actually, when I say both are correct, it's because it depends how you measure K. And when you measure K, how you scale it back to find the K value. The K has always been found in such a way that they use the velocity of the higher part, not the lower part. Okay? So the higher, the K that we find in the textbook and so on, alright, is always measured based on the velocity in the larger pipe. Alright? You could redo and find your own set of K for a smaller pipe. Alright? But unlikely you do that. So you follow the convention used in the textbook, and K is always based on the velocity of the larger pipe. Okay? So plus, alright, so V1 is faster than V2. Okay? So it's always, so this is always based on the higher V here. Okay? So here, K contraction. Based on V2 or V3? Okay, V3. Okay? So again, the contraction, this K for the contraction is based on that higher one. Right? So between V2 and V3, obviously V3 is higher, it's contraction. So that's why it's here. Okay? Alright, so that's the minor losses and one more. Plus Km3. V3 squared over 2G. Alright? So this one is normally 1. Okay? Sometimes they don't tell you, so you need to know that it's 1. But normally they don't tell you. Okay? So that is the minor losses for that part. Alright? Entry, first pipe, expansion, second pipe, contraction, third pipe, and then entry. Alright? So that is for pipe in series. Okay? Any questions? Alright. So this one you have to remember. Alright? Velocity always based on higher velocity. Okay? Write on your shoe or something, I have to write. That's the convention. Let's see. Alright? So I didn't go too big. Okay, so if it's a sudden alright, so if you have a sudden contraction or sudden expansion, there's a lot of turbulence or eddies or losses at the corners here. That's on the picture. And basically this is a plot of K versus D on D. Alright? So obviously the bigger the diameter ratio is, obviously the bigger the diameter ratio is, the bigger the difference between D to big D over small d, which means you go smaller here, right? You get a lot more losses. Yeah, okay? So if D on D is 1, it's a straight pipe, there's no minor losses, that's why it's 0 here. Alright? So, and it goes up here. For the expansion and for the contraction. This is KL. Okay. Alright? If you here quite high, up to 1, expansion gets a lot of losses, contraction not so bad. Alright? If you want to do, if you want so much losses, then you can put a diffuser in there. Then the losses, KL, is a function of the angle. Alright? That is, the best you can do is around 7 degrees. Alright? 7 degrees, you get the least losses, 1.2-ish, 0.25 or something. Alright? And if you go any faster, it goes higher. Alright? Why I say that? Why is it 7 degrees? It's because if you diffuse at 7 degrees, alright, in your other very gradual diffusion, the turbulent flow doesn't actually separate from the wall. No separation. Alright? So at this part here, there's no separation. Okay? But if you diffuse at any angle faster than that, the flow will not follow your wall. It will separate, and when you have separated flow, the stagnant region there will recirculate and will dissipate a lot of the energy. Alright? So I draw in picture. Okay. So, but 7 degrees means your diffuser will be very long. It's gradual. Alright? So, where's my picture? Postpone. Where's the picture? Okay. So, diffuser. This angle here, 7 degrees. Alright, for no separation. Alright, so if it's larger than 7 degrees, you expect the flow to separate here. Alright, this is the streamline. And then there'll be a lot of recirculation here. Stagnant, S-T-A-G-N-A-N-T, recirculating region. Alright, where will energy dissipates? Is dissipated. Alright, so if you want to bother to do a diffuser and you want to do a good job, you have to have a fairly long diffuser so that it separates it diffuses at a very gradual angle. Okay, save this one. Any questions so far? Alright, save. No. Okay, so as you can see, in both cases, the KL is based on the, in this case, the KL is based on the V1, the higher velocity. In here, you see the KL, the velocity is always based in the smaller pipe, this velocity, and in here is this velocity. Okay? Another one? Any other thing? No, I think that's it. View. Okay. All right. So KL is minimum. This is a diffuser. All right. Any questions so far? KL is minimum. For 7 degrees, no separation. Okay, no separation. Yeah, so stack STAG, yes, recirculating. Recirculation. Alright, so the flow just goes round and round like the stagnant region. Alright. The main free stream go out here. Alright. Any questions? Okay, so the final thing for discussion today is pipe in parallel. Okay. All right. So pipe in series, minor losses we've covered. So we covered those two things. All right. Pipe in parallel. All right. Okay. No. This is branch 1, this is branch A, this is branch B. Alright, this is point 1, this is point 2. Alright, P1 on row G plus V1 squared on 2G plus H1 plus H turbine, H pump, alright, is equal to, in this case no pump, so don't worry about that, P2 on rho G plus V2 squared on 2G plus H2 plus head loss plus head turbine. Alright, so if I went from 1 to 2, path A, alright, this equation applies, but HL is equal to HL, comma A, alright, down path A. Okay or not? Is that right? Okay. If I went from 1 to 2, alright, the liquid going from 1 to 2 got two options. You can go to path A, you can go to path B. At the end, it comes to 2. Alright now. Alright? So if I choose path A, that equation applies, everything except the head loss. I must put the head loss in path A. Is that right? And condition, initial condition all same. Alright? I didn't put it, if you go to 1 to 2 again, to path B, everything is the same, except you go down path B. HL is equal to HLB. Okay or not? So if I took the same, these two, so I formed two equations here. Alright, I didn't bother writing, you can write if you like. Alright? This one, exactly there, except where HL appears, you put HL in. This one, exactly everything same there. HL appears, you put HLB. Okay or not? Then you subtract those two equations in your head, what do you get? You get nothing. Alright? You get HLA equals HLB, isn't it? Alright not? Everything is the same. Alright? Two equations are identical except for one of those things. So those things, what you end up with those two things subtracting equals to 0 or HLA equals HLB. Okay or not? Need to do or not? Alright? Can you see? Alright? So everything is the same. Alright? From going from 1 to 2, either path A or path B, everything is the same, so therefore the HL must be the same. So everything else is the same. Right? Okay. Alright? You know, you go do this for homework. Go to path 1, put HLA here. Do this one, HLB there. Subtract the 2. You get HLA minus HLB equals 0. Alright. For those who don't believe. Okay? So what it says here is that the head loss is the same. In other words, okay, HLA equals to basically, let's say this is a simple pipe, not so complicated first. F A LA over DA VA squared over 2G. Is that correct? Plus sum of KL VA squared over 2G. Here be FB, therefore this is equal. FB LB L over D B squared over 2G B plus if there's any minor losses, VB squared over 2G. Is that okay? So pipe A, the losses, and pipe B, the losses must be the same. I know. So, but they don't have to be the same pipe. Okay? Obviously, they don't have to be the same pipe. Alright? If one pipe is more problematic, in other words, the diameter is smaller, alright, the F is higher, or more minor losses, then you can expect the velocity here to be less. Alright now, compared to here. Okay? Example, what I just said. Basically, this must equal to this. So if FA is high and KLA, this is B, KLA is also high, so you can expect VA to be low. Okay or not? Alright? Or vice versa. Alright? It's basically what I'm saying here is the water or the fluid will choose the path of least resistance. Okay? So if it's very hard to go down path A and very easy to go down path B, more fluid will go down path B and less fluid will go down path A. Alright? Or vice versa. Okay? Is that alright? Example? Right now. Alright? Example is now and then after a good, hopefully you don't end up to do it too young. After a good long life of parties and alcohol and other things and tobacco and so on. Okay? Normally is the artery or the, I don't know, artery is okay? Alright? No, I can't remember the name. Alright? Normally one or a few of the main arteries, alright, or veins, I think the arteries, alright, will get clogged. Alright? Okay? So okay, so this artery, alright, and they got special mucus and all that there. Alright, so after all your years of partying, having good life and all that, eating high cholesterol food and so on, alright, the cholesterol will line up this one. Hey, quiet please. Hey, this one's serious, this example, not fooling around. Alright, so after years of fooling around, this plaque, this cholesterol and all that, or plaque here, alright, it actually hardens. Alright? When you're young, the time it's not hardened, so it actually can erode away. It's actually well lined with agents that will break it out away so that it's nice and slimy and doesn't harden. Alright? But after a while it hardens. Okay? And when it hardens, it gets narrower and narrower. Alright? Okay? So when it's narrow, alright, you expect, quiet please, you expect the diameter to go up and this one go up. Alright or not? Alright? Then, diameter go down. Alright? So you expect this one to go down. Alright? For given pumping capacity of your heart. Alright? Okay? Because your heart can only pump that hard. Alright? So for given pumping capacity, you are decreasing the diameter, increasing the friction factor, because now the pipe is very rough and hard. Alright? This one goes down. Is that alright? Okay? So then in severe cases, they saw your chest bones open. Alright? And then they put it apart. Okay, it's very messy. After that, they have to put it back and staple it back together. It's messy. So I advise you try to keep your heart in good shape. Alright? Open heart surgery is like this. Your heart is behind your rib cage. How else to get to it? Alright? They take a vein. Quiet please. Hey, this is important lah. They take a vein from your leg. Alright? And they graft it on here. They call it bypass. Alright? Okay? So this vein is still healthy. Hopefully they take a healthy vein. No point taking a... Okay? So they take a healthy vein. So now it becomes a flow in parallel, isn't it? Parallel pipes. Alright? So this one is still healthy. The diameter is good. The F is down. Alright? So they don't bother cutting this away. They still leave it there. But only a small amount goes here. The large amount goes down here. Alright? Because the head loss between here and here is the same. Alright? Down the down the path with the narrow and very high friction, only a little bit. So m dot is small. Here, m dot is large. Okay? So that's the example there. Any questions? If not, I think I better stop here. I think next class one comes in. Huh? Huh? The pressure drop is actually the same. If the diameter is small, then you need more pressure to drive the same amount of flow rate through. Okay? Outside.